Welcome to TennaTalk, a journey of discovery about all things antenna. TennaTalk is a production of the Antenna Whisperer. That's me, Rudy Wiedemann, K7RAW, and it is generously supported and sponsored by the Las Vegas Radio Amateur Club. This podcast will be in two parts. 4 Alpha, which will be laying the foundations of impedance matching with LC circuits and how to navigate around the Smith chart so that you can move from pretty much anywhere to the ideal, perfect, pure 50 ohm resistance sweet spot in the middle. And that'll be followed by 4 Bravo, which will be a podcast about how to navigate the Smith chart using SimSmith and its effect on the SWR curves and how to interpret the Smith chart results to see how you can get the best performance and what kind of performance you can expect over what kind of a band. And you'll see how powerful SimSmith is in this whole system. And we'll do a bunch of examples along the way. So with that said, let's get going. The agenda for this podcast will first be a refresher on impedance concepts. And then we'll move into an introduction of Smith charts, and then component pathways and sequences along the Smith chart. And we'll see some examples using some LC and CL networks, meaning high pass or low pass filter type networks, and capacitor and inductor networks for special cases. And then we'll move to pi and T networks, and finally popular miniature auto tuner using discrete L and C components and combinations of those to achieve a match. The idea is to get you comfortable with how LC circuits work, to do impedance matching, and how to navigate them in the Smith chart. So with that said, let's get going. As a quick refresher to impedance, let's first talk about what is impedance. Impedance is a complex number denoted usually by the letter Zulu, Z, and it's comprised of the total resistance plus the reactance, and that's J. That means it's an imaginary number. This is the real part, is the imaginary part. Think of that as plotting it in 2 axes if you want to, horizontal and vertical axes. Now, in podcast 3, I mentioned that this was the antenna radiation resistance, and that's not technically true. The ohmic resistance and radiation resistance, what this total is about, but most of the time the dominant value is the radiation resistance if you've got an efficient antenna and you don't have a lot of ohmic resistance in there. Both the R and the X values are in ohms, because it resists AC signals just like it resists DC signals. The total is RT, which is the real part of the complex impedance, and as I mentioned, it's a combination of the load or radiation resistance plus the O or ohmic resistance, and that ohmic resistance is often negligible, but it's still there. Now, values that are closer to 50 ohms require less lossy LC values. So what we'd really like is a Z equal to 50 ohms plus a 0JX. And that gives us a perfect impedance match at each interface. And remember, it's at every interface that you have. Rig to coax, coax to any balun or UNUN, and then the UNUN or balun to the antenna itself. The VSWR is derived from the ratio of the resistance to 50 ohms, whether it be above it or below it. An R of 25 ohms or an R of 100 ohms will give you the same SWR of 2.0. Reactance, the JX value, which is the imaginary part of the complex impedance, is another factor that we look at, and that tells us how resonant the antenna is as opposed to the actual loading it provides. A negative JX means that the antenna is capacitive or shorter than resonant typically. A positive JX means the antenna is inductive or sometimes longer than resonant, and longer meaning electrically longer not necessarily physically longer. So here's the infamous Smith chart. Now don't get too shook because we're going to walk our way through this fairly carefully. The red here is impedance and the blue is admittance, okay? And you'll see that you'll have red circles. You can see the red circles coming out like bubbles from this side. Those are impedance side of the Smith chart. Anything in blue, these bubbles are admittance bubbles, okay? And they're comprised of the conductance and the susceptance, as we'll see here in a moment. Now, you'll notice that the equator here on a Smith chart is a resistance path or a resistance scale. 50 ohms is in the middle, and as you move towards 9 o'clock, it becomes a pure dead short. As you move towards 3 o'clock position, it indicates an open, wide open end of your feed line or of your impedance match point. So realize also that it goes up and down from the 50 ohms logarithmically. So 25 ohms is not halfway. It's actually much shorter, much closer. So it'll go from here to like 25 to 10 to 5 to 2 to 1, etc. And from here it'll go to 100, 200, 400, 500, 1000, 2500, etc. very quickly. So it's a logarithmic scale. If you see a Smith chart plot on your nano VNA, for example, that's along the horizontal, then you don't have any kind of reactance, okay? There is no positive reactance or negative reactance. Up here above the equator, you have a positive JX value, okay? That means the antenna is generally inductive. Below, it's capacitive, all right? And we'll get to these here in a second. But also, if you want to plot a constant SWR, this is an example of a circle that is the constant SWR circle. So if your Smith chart at the particular value you're looking at gives you a position that's within the circle, then you are within that SWR. The closer to 50 ohms, of course, the closer to 1.0 SWR that you can achieve. Now, what are these S values all about? S11 here and S11, and these bars means the absolute value, okay? And that means all power is absorbed in a short. Here, all power is reflected in an open. And you want to be right in between. You want everything transmitted, okay? Nothing absorbed, nothing reflected. And so you'll also see these values sometimes referred to as scattering values. That's why they're called S values. Now, realize that sometimes in the original days when you used the actual physical paper chart of a Smith chart, you would very often normalize the Smith chart to 1 ohm at the center. So you divide everything by 50. You divide all of your R and JX values by 50, and then you'd navigate and plot them here. Then you'd then multiply back by what is called your characteristic impedance, which is 50 ohms. In most cases, because that's what your rig is set to, and that's what your most coax are used at, is 50 ohms. So that's a little bit about the Smith chart to begin with. So don't get too shook. Just take a look at this for a little bit, and it'll start to make sense in a moment. Now, some of the resistances of typical antennas are listed here. You'll see that inverted V gives you a pretty nice natural impedance of 50 ohm match. And you'll see that short quarter wave verticals that are often used on mobile rigs are less than 50 ohms. And a short whip mobile will maybe be a lot lower resistance than that. And that's why you have to, your inductive, or excuse me, your capacitive and you'll see it have some negative J value to it as well as being a low resistance. So that's why you need a lot of inductance and maybe some capacitance in some cases. So with that said, let's move on to case. Let's start with using a 9-to-1 UNUN alone. No tuner, no LC circuits per se, just an UNUN, which is an auto transformer. And let's say we are at the 22 to 25% from the end feed point on a dipole for an off-center fed dipole. And the reading on our Smith chart for that frequency, and it'll be different for every different frequency, remember, but for, let's say, 20 meters, you want to operate this thing on 20 meters, it gives you a readout of 450 ohms of resistance and 0 JX value for reactance. So that'll put you right about here on the Smith chart. Now you want to move to right here on the Smith chart, which is obviously the sweet spot of 50 ohms and no reactance. How do you do that? You can do that with an UNUN alone. So you look at 450 divided by 50 and realize that's 9-to-1. Well, guess what? Then I need a 9-to-1 UNUN to convert it, to down convert the resistance here down to 50 ohms. And as you may recall from podcast 3, a 3-to-1 ratio, 1, 2, 3 turns on the antenna side, and that's the input to the system. Okay, that's our starting point, is always on the antenna side on the Smith chart. Just remember that. To a single coil here into the output to our, let's say, our PL259 or BNC connector to the radio or to the coax. And so that's what will take us from 450 ohms straight to 50 ohms very, very nicely. So now let's take a look at the different concepts of impedance and admittance and all the things that make up those factors. So first of all, as we said, all LC components are inserted from the antenna side and built up towards the rig. The resistance is a series component, always positive, all right? The reactance, the X value, impedes the AC signal. It tends to impede the AC portion of the signal, the wiggling portion, if you will. Impedance is therefore the resistance and the reactance summed together. Now another concept is conductance, which is actually the inverse of the resistance in a way. It is a shunt component, it's always positive, and it really encourages the flow of current. So G is the inverse of R. Similarly, susceptance B is the inverse of reactance. It allows AC signals to pass as opposed to impeding them. And admittance Y is the conductance plus the susceptance, and that is the inverse of impedance. So impedance inverse is admittance, resistance inverse is conductance, and reactance inverse is susceptance. So that's just different mappings from different sides of the Smith chart, as you'll see here in a moment. So these are circles of constant resistance. Let's start there. You'll see these as red circles on the Smith chart. And you'll see the blue one goes right through our midpoint of our Smith chart, right through the midpoint of our equator axis, right there at dead center. That's a constant 50 ohm resistance circle. This might be a constant 25 ohm resistance circle, and maybe a constant 10 ohm resistance circle. The inverse of resistance is conductance. Resistance are usually associated with components that are in series, usually with the center conductor of your coax, and conductance are usually associated with components that are in shunt mode or across from the center conductor to the ground, to your braid or your shield. And so you'll see that this is the inverse of resistance, and you see constant conductance here, constant conductance, constant conductance. The horn-shaped curves on a Smith chart are reactance that are those horns coming from the right side, and this is constant reactance of maybe 50 JX, this might be 100 JX, okay, a positive JX, and negative JX down here, okay? And these are curves or horns of constant susceptance, which is the inverse of reactance. All right, and so there's a constant positive susceptance curve and a negative susceptance curve. You'll see how this maps out in the Smith chart in a moment. So again, this is the Smith chart, and if you look carefully, you'll see the red circles, the constant resistance circles in red. If you look closely, you see constant conductance circles in blue, all right? And then if you look closely, you see the red horn-shaped reactance curves and the blue horn-shaped susceptance curves, positive and negative, going down. And here's some of the rules on which how we navigate. Series components will move you clockwise or counterclockwise along the red resistance, because as I said, series components give you resistance. Okay, so that's the red circles. So if I were to move along a constant 50 ohm resistance circle, I'd be moving this way, clockwise or counterclockwise along the 50 ohm resistance circle. A shunt component moves you clockwise or counterclockwise along the blue conductance circle, because a shunt wants to conduct electrons from the center to the shield. So those are the configurations. When you're shunting a component, you're moving along the blue circles. Now for the horn-shaped curves, the red horn-shaped curves are the reactance curves, positive and negative from the right-hand side. And the blue are the susceptance curves, positive susceptance, negative susceptance. And you'll see that as you move along a constant resistance circle here, you'll be cutting through different reactance horns, and different levels of reactance. As you move away from 50 ohms in the middle, you'll get more and more positive reactance, or you're mapping more and more negative reactance as you're on constant resistance. So still 50 ohms all the way around, but the reactance is the component that changes. This allows us to move in either resistance or reactance on this side, or conductance and susceptance individually and separately on this side through different paths. So hang on, bear with me. It'll actually start making a lot more sense as we have some examples. So there are 8 different configurations for LC circuits. You'll see here this is a low pass filter. These are both low pass filters, one with the inductor after the capacitor, because remember, we're adding everything starting from the antenna end towards the rig. So the capacitor is added first, then the inductor. Here the inductor is first, then the capacitor. Okay, these are high pass circuits where the inductor is first, and here's the inductor is second after the capacitor. And you'll see in a moment how the different paths change. We have similar paths that we can do with a capacitor in terms of, I won't call it high pass or low pass anymore, but whether one capacitor is ahead of the other capacitor or behind the other capacitor. Same thing with inductors, ahead of one inductor or behind one inductor, as seen from the antenna to the rig. This is just a chart that looks at it in a different way about keep-out areas, because if you have this kind of a circuit configuration, then it can only actually impedance match in this part of what I might call a yin-yang curve, all right? And it'll only operate in the clear area. It cannot help you match in this area. It won't work. and similar to the other styles, other configurations of the LC circuits, high pass, low pass. All right, and for capacitor circuits and inductor circuits, here are the inductor circuits. You can see the forbidden areas here, and you can see the allowed areas of matching here. So let's see some examples of all this. So let's take a look from the perspective of a couple points off of the center point. That is not ideal. Something other than 50 ohms and 0 reactance as starting points. And we're going to look at 6 different points. We're going to look at 1, 2, 3, 4, 5, 6. 6 points away from the sweet spot. And notice up here I've got a nice little chart here that maps out your different directions. If you want to go along a clockwise resistance circle, those red circles, you'd use a series L. If you want to go counterclockwise on a conductance circle, okay, going this way, then you'd use a shunt L. A counterclockwise resistance would take you on a series C. So counterclockwise here's a resistance circuit going counterclockwise, that's a series C. And a shunt C would give you clockwise along a conductance circle, which means going this way. So there's your 4 different combinations along the 2 different circles. And let's see what this does for us. So here I've got a situation where I'm starting from a impedance of 10 and 0 reactance. That's perfectly resonant, but it's a resistance of 10. That means it's a 5-to-1 SWR, because 50 divided by 10 is 5, right? So I need to get it over here to 0 reactance, but I can't get there directly, all right? Now, I could if I had the appropriate UNUN, but most of the time you wouldn't use an UNUN because most of the time you're not perfectly 0 reactance. You've got some reactance, either positive or negative reactance in the system. So from here, I would navigate clockwise on a resistance circle, okay, and that would mean a series L that looks like that over here. Remember, I'm going from the antenna side and adding it towards the rig side. And then I need to move down a constant conductance circle clockwise. And clockwise on a conductance circle means a shunt C. And there's my shunt capacitor across my 2 leads. And that'll get me to 50 ohms. The other way to get there is counterclockwise on a resistance circle with a series C, and then counterclockwise on a conductance circle. Counterclockwise and conductance is a shunt L. And those are 2 different ways to get there. Now, if I was off of the pure resistance axis here, then you would want to use different values of that. I might be, if I were starting here, then it would be a smaller series L component. Okay? Now, if I were going from here, I would prefer going short distance as possible because a smaller LC values gives me a more efficient match than going all the long way around here like so. So let's look at a different configuration now. I'm starting from a high pure resistance, no reactance, and I use a shunt L to go counterclockwise on a conductance curve, okay, until I get to a nice 50 ohm resistance curve right up here. And then I navigate down towards my 50 ohm perfect resistance with a series C. Likewise, I could go the other direction with a shunt C going clockwise along a conductance blue circle, and then going clockwise on a resistance circle with a series L component. Now, what if you're up here at 10 ohms and a positive 50 reactance? Well, you could go one of 2 different directions. You could either go down here with a series C and then a shunt C, Or you could go down this way with a shunt C and a series C in that sequence. Now, usually you're not exactly in this perfectly balanced point. You're usually over to one side or another. Well, you would then favor the path that gives you the shortest distance because it'll give you the smallest component values for the best efficient match. What if you had a negative reactance? You started with a negative reactance. Well, you could either start with a series L followed by a shunt L, okay? Or you could start with a shunt L followed by a series L. They would both get you to the same place. And again, if this was off center, over to the left or to the right, then I might favor one versus the other because of the lower values it gave me. And so here we see all four configurations, all four conditions mapped out on the different paths, and you can see here the different paths, 8 different paths that we could use, and each one of these little arcs is in color coded here, and you can see how that all works. Okay, so now let's take a look at different network configurations. We did talk a little bit about high and low pass and shunt components before or after the series components. Okay, we'll take a look in a moment at pi networks and T networks. And then we'll look at discrete and continuously variable components, and we'll look at an example of how one of these little automatic discrete LC auto tuner networks operate. A pi network looks like the Greek letter pi, as you can see above here. Very often it'll have the inductor in series and the capacitors in shunt configuration, because that's most favorable for navigating the shortest distance on the Smith chart. Likewise, you can have a T network. Of course, this looks like a T with the inductor in the shunt configuration for those paths that give you most efficient movement along the Smith chart for the shortest distance. In other words, most efficient conversion match. Now, let's wrap up by talking a little bit about the famous ATU100 by N7DDC. Now, we're looking just at the RF portion of this. We're not looking at the microprocessor, which is over here typically. We're mostly interested in the L's and C's and how this thing works. So let's first look at you have the RF input and the RF output. All right, so here's your jacks. They go through, on the RF input, goes through what's called a binocular ferrite of 2 leads going through the 2 holes in a kind of a flattened ferrite. And all this does is it picks up a little sample of the signal. And that sample then gets divided down, and then you have these 2 diodes back to back to actually measure the forward and reverse currents. And those forward and reverse currents are then converted into signals, and this little green bus bar goes back to the microprocessor, giving it 2 inputs, 2 analog inputs of the voltages, the forward voltage and the reverse voltage. Now, how does this work as a tuner? Well, you'll see here are all of the different inductors, 4.4 microhenries, 2.2, 1 microhenry, all the way down to 0.05 microhenries. And you'll see that they're in series. And you'll go, oh my goodness, how are we going to control these? These are all in series. They're all stacking up together to be somewhere almost twice the value of the maximum one. Well, guess what? These are relays, and they're used to short out selectively the inductors we don't want in the path. So what'll happen is if we've got, let's say the first 2 shorted out, the current goes through the relay instead of through the inductor. And then this one, the relay is open, it's not shorted. So we're adding 0.22 microhenries. And so you can see that by shorting or not shorting the inductors, we can make any configuration out of these 7 inductors that you have, and it's typically 7. Now on the capacitor side, here's our capacitors from 10 picofarad all the way up to 1,000 picofarad. And you can see it goes down kind of in a logarithmic scale, half, half again, roughly half again, roughly half again. And how does this work? Well, these solenoids, these relays, operate to either connect this capacitor in series, okay, or it's wired in series with the capacitor, and these will cut it out. So each relay is in series with the capacitor going up to the common point, okay? And if you look very closely, you'll see that the common point is right up here, okay? And so this is all tied in together. So you're adding capacitors, and all this guy does here is it switches whether the capacitor is on the antenna side of the inductor or on the rig side, okay? And these are always in shunt mode, and these are always in series. So hopefully that gives you a little idea of how typical auto tuners using discrete inductors and capacitors operate, whether it's an LDG, an SGC, or any internal auto tuner, a little miniature auto tuner like the ATU 100, they all pretty much work the same way. They use different ranges of inductors and capacitors, sometimes to get a larger range of matchup capabilities, but fundamentally they all work the same way. So the next podcast is going to be the second half of this, which is for Bravo. And that's where we'll be driving SimSmith around. We'll be actually using some of these examples, and you're going to see it being done live, and you're going to see the effects on SWR, on the Smith chart, and you'll be able to see all of this in color and with a whole bunch of really cool tools. So I encourage you to study this first until it starts to make sense, and then watch for Bravo, and that will actually anchor all of this in, and it'll allow you to play the same games. If you download SimSmith, you can play the same games and drive it around, and it'll give you a tremendous amount of power, because from there we're going to show you how to import your scans from your Nano VNA right into SimSmith and analyze it and tune it and see how it'll perform on any band, and then also be able to take data straight from modeling programs like EasyNet straight into SimSmith and see how your antenna would perform and what you might have to do to adjust the antenna and get it to maximum peak performance. So with that, please click the like button and the bell icon, and please subscribe if you want to be notified about future videos. I hope you enjoyed this. Please make comments below of what you liked, what you understood, anything that was confusing, and I will try to answer that in future videos. But until then, 73, and I hope you enjoyed this video and have a great day. Take care.